Right now, inside a planet 4.4 billion kilometers from where you are sitting, it is raining diamonds. Not metaphorically, not in some distant galaxy. In Neptune, one of the 8 planets of our own solar system, pressures so extreme they shatter. Every intuition you have about matter are tearing methane molecules apart, liberating carbon atoms, and compressing them into diamonds that sink through the planet's interior by the trillion. Scientists confirmed this in a laboratory in 2024. And here is the part nobody talks about. Jupiter and Saturn may be doing something even stranger, melting those same diamonds into liquid oceans. But the most unsettling question is not what is happening out there. It is what would happen here if the rarest stone in human civilization suddenly became as common as gravel. Hey, if you have ever wondered why we spend so much of our lives chasing things the universe gives away for free, this is the episode for you. We are about to go deep into the science, the economics, and the completely ridiculous thought experiment of a world where diamonds are just another building material. And I promise, by the time we are done, you will never look at a ring the same way again. If that sounds like your kind of journey, hit the like button, subscribe so you never miss one of these, and let us get into it. In 3, 2, 1, liftoff. Let us begin with a number. 140 miles. That is how deep inside the Earth a diamond has to form. Not 140 feet, not 140 stories, 140 miles straight down into a layer of the Earth called the lithospheric mantle, where temperatures run between approximately 900 and 1300 degrees Celsius, and pressures crush everything around them at roughly 45 to 60 kilobars, which is to say 45,000 to 60,000 times the pressure of the atmosphere you are breathing right now. Hold that number in your mind. You will need it later when everything changes. Down there, in that furnace, carbon atoms, the same element that makes up the graphite in a pencil, the same element at the center of every organic molecule in your body, are being compressed into the tightest, most geometrically perfect arrangement that nature allows. Each carbon atom reaches out and bonds covalently to exactly 4 neighbors, forming a tetrahedral structure, a tiny pyramid of atoms repeated trillions upon trillions of times in every direction. That repeating pyramid is not just a curiosity of chemistry. It is the reason a diamond cannot be scratched by anything except another diamond. It is the reason that a diamond, sitting on a countertop, conducts heat away from your fingertip 5 times faster than silver does. It is the reason that the Mohs hardness scale, which runs from 1 to 10, places talc at the bottom and diamond alone at the top, with nothing beside it, nothing approaching it, nothing even in the same conversation. That is what a diamond is, not a symbol, not a marketing category. A carbon atom that found 4 friends and never let go. But here is the part where the story becomes strange, and it becomes strange almost immediately. Because for something so physically extraordinary, the hardest natural substance ever identified, the best thermal conductor of any solid material at room temperature, a material so chemically inert, it barely reacts with anything, diamonds have spent the overwhelming majority of human history doing almost nothing useful at all. They have spent that history sitting in rings, dangling from necklaces, locked in bank vaults, buried in the fingers of statues, traded as currency between warlords, cut and polished, and placed behind glass, where people press their faces and whisper about how much they are worth. The most structurally exceptional material the Earth produces has spent millennia as decoration. That is not an accident. That is a construction. And, to understand how thoroughly constructed it is, You have to go back to a place that has nothing to do with chemistry at all. You have to go to South Africa in 1888. That year, a man named Cecil Rhodes, who had already made himself enormously wealthy by controlling water pumps during the diamond rush at Kimberley, engineered the merger of every major diamond mining operation in the region into a single company. He called it De Beers Consolidated Mines. The logic was not complicated. If one company controlled the supply of diamonds coming out of the ground, one company controlled the price. And if the price could be controlled, the illusion of scarcity could be maintained indefinitely, regardless of how many diamonds were actually being pulled from the earth. De Beers did not have to make diamonds rare. They just had to make sure that the market never saw more of them than was carefully rationed. For the next 100 years, De Beers operated what was, by any reasonable economic definition, a cartel. They stockpiled diamonds. They controlled the channels through which rough stones reached cutters and jewelers. They marketed their product not as a luxury item, but as a requirement, a physical object without which certain human experiences could not be properly completed. When new diamond deposits were discovered in Russia in the 1950s, De Beers negotiated directly with the Soviet government to bring those stones into the existing distribution system rather than allow them to flood the market and collapse prices. When Australian mines opened in the 1980s and began producing enormous volumes of lower quality stones, De Beers absorbed the supply. The system was not about mining. The system was about control. And then came the advertising campaign that cemented everything. In 1947, an advertising copywriter named Francis Geraghty, working for the NWA agency on behalf of De Beers, wrote 4 words that would become arguably the most successful advertising slogan in history: "A diamond is forever." The campaign was not designed to sell a product. It was designed to eliminate the secondary market. If diamonds could be resold freely, as one might sell gold or silver or any other valuable commodity, the controlled scarcity would collapse. People would buy diamonds, wear them for a few years, and then sell them back into the market at prices that reflected their actual abundance. But if the cultural narrative established that diamonds should never be resold, that to sell one was to betray the love it represented, the secondary market would dry up. And it did. "A diamond is forever" is not a description of a gemstone. It is the cleverest supply management strategy ever disguised as romance. Within a decade, the engagement ring went from being a regional tradition with variable cultural significance to a near-universal Western requirement. By the 1960s, more than 80% of American brides were receiving a diamond engagement ring. The figure is often cited with something like awe, as if it reflects an ancient human preference for sparkle and commitment. It does not. It reflects a marketing campaign that ran for 30 years with extraordinary precision and nearly unlimited resources. The tradition that feels like it came from the Elizabethan court or the pages of Shakespeare was invented during the Truman administration by an advertising agency in Philadelphia. None of this is cynical observation for its own sake. It matters because it establishes something essential. The price of a diamond has almost nothing to do with the diamond. It has to do with the system of distribution, cultural construction, and controlled scarcity that surrounds the diamond. Take away that system, and a diamond is not worth more than its physical properties justify, which is to say, it is worth whatever someone would pay for the hardest, most thermally conductive natural material ever discovered, which, as we will come to see, turns out to be quite a lot, just not in the way the market currently imagines. But before the thought experiment, the physics. Because you cannot understand what abundant diamonds would mean for civilization until you understand what a diamond actually does, and why those properties are extraordinary in ways that have nothing to do with how light refracts through a cut facet. Start with hardness, because hardness is the most famous property and also the most consistently misunderstood. When people say that a diamond is the hardest natural substance, they tend to imagine hardness as a single, simple property resistance to being dented or squashed. But the Mohs scale, developed by the German mineralogist Friedrich Mohs in 1812, measures something more specific: resistance to being scratched by another material. A material at level 10 on the Mohs scale cannot be scratched by any natural substance below it. Diamond sits at 10, not 9.9, not approximately 10, 10, with nothing else beside it. Corundum, which is the mineral family that includes sapphire and ruby, sits at 9. The difference between 9 and 10 on the Mohs scale is not one step, it is an exponential gap. Corundum requires roughly 140 times more force to scratch than topaz does, and diamond requires roughly 3 to 4 times more force than corundum. In practical terms, this means that diamond is the only natural material capable of cutting, grinding, drilling, or abrading every other substance on Earth. Every other cutting tool eventually meets a material that defeats it. Diamond does not. This is not merely theoretically interesting. It is the foundation of an entire industry. Right now, industrial-grade diamonds, stones too clouded, too small, or too poorly formed to be gemstones, are already embedded in the tips of drill bits used to bore through granite, limestone, and reinforced concrete. They are crushed into micrometer-sized, abrasive powders used to polish semiconductor wafers to tolerances of a few nanometers. They are set into the teeth of saw blades used to cut highway asphalt. Approximately 80% of all diamonds produced worldwide by weight, not by value, by weight, go directly into industrial applications. The gem trade is, in terms of actual diamond volume, a minority use. The majority of the diamond produced by mining already ends up in newts. It is just that the machine-grade stones are brown and grey and cloudy, and nobody is writing songs about them. The reason industrial diamonds are not used more extensively is not that they fail to perform, it is that they are expensive. A diamond-reinforced concrete mixed diamond aggregate embedded in the binding matrix of a building's foundation would create structures with compression, resistance, and vibration damping far beyond anything conventional aggregate provides. Engineers know this. Materials scientists have studied it. The reason your home's foundation does not contain diamond is that the economics make it completely impossible. A kilogram of rough industrial diamond costs hundreds of dollars. A kilogram of gravel costs pennies. When diamond is as common as gravel, that calculation reverses instantly, and the conversation shifts from whether to use diamond aggregate to how much of it to use and in what proportions. That is the lever this episode is going to pull. But first, thermal conductivity. Because thermal conductivity may be the physical property with the most profound practical consequence of all. At room temperature, diamond's thermal conductivity has been measured at approximately 2,200 watts per meter per Kelvin. That is the rate at which heat flows through a slab of material. Higher is better when you want something to carry heat away from a sensitive component quickly. Silver, which is the best metallic thermal conductor at room temperature, measures approximately 430 watts per meter per Kelvin. Copper, which is the standard material used in heat sinks inside every computer ever manufactured, comes in at approximately 400 watts per meter per Kelvin. Diamond outperforms copper by a factor of 5.5. It outperforms silver by a factor of 5. And for monocrystalline synthetic diamond, enriched to be nearly pure, carbon-12, the isotope most efficient at conducting heat, the measured value climbs to approximately 3,320 watts per meter per Kelvin, making it not just the best natural thermal conductor, but the best solid thermal conductor of any substance ever measured at room temperature, period. This matters for a reason that is immediately practical and not at all abstract. The single greatest limitation on modern electronics is heat. A processor in your laptop or smartphone generates heat at a rate that, if not managed with extreme precision, would destroy the chip within seconds. The entire architecture of modern computing, the fan systems, the heat pipe networks, the thermal paste between chip and cooler, the ventilation slots in every laptop chassis exists for one reason: to get heat away from a transistor fast enough that the transistor keeps working. The smaller you make a transistor, the hotter it runs per unit area, and the harder the heat management problem becomes. This is one of the central physical constraints currently slowing the progress of computing hardware. Engineers designing the next generation of processors are not primarily limited by their ability to etch smaller transistors. They are limited by their ability to remove the heat those transistors generate without destroying them. Diamond heat sinks, thin slabs of diamond placed between a high-power chip and a cooling system, are already used in extremely specialized applications: high-power laser diodes, military-grade electronics, certain scientific instruments. They are used precisely because nothing else removes heat as effectively. They are not used universally because they are extraordinarily expensive to produce. A single diamond heat spreader for a research-grade laser system can cost more than the entire rest of the laser. If diamond were common enough to be used routinely as a thermal interface material in consumer electronics, the thermal management problem in computing would not disappear, but it would shrink dramatically. Chips could run faster without overheating. Batteries would last longer because less energy would be wasted as heat. Devices could be smaller because they would not need as much space dedicated to cooling infrastructure. The thermal conductivity of diamond is not a laboratory curiosity. It is a solution to one of the most pressing engineering problems of the 21st century, sitting behind the barrier of price alone. There is also chemical inertness. Diamond does not corrode. It does not react with water, with most acids, with alkalis, or with most chemicals under standard conditions. It is impervious to the electrochemical processes that rust, iron, pit copper, dissolve limestone, and degrade most other materials over decades of exposure. This makes it ideal for any application where long-term durability in a chemically hostile environment is required. Diamond-tipped surgical instruments are already produced for specialty procedures, certain ophthalmological surgeries, certain neurosurgical applications, because a diamond edge is both sharper and more durable than any steel edge. When a diamond scalpel is resharpened and reused, it maintains its geometry in ways that metal does not. The edge does not deform. Under sufficient abundance and at low enough cost, every operating room in the world would use diamond-edged instruments as standard equipment, not as a luxury confined to the wealthiest hospitals. Diamond electrodes represent a less famous but equally significant application. Boron-doped diamond in which a small fraction of carbon atoms are replaced with boron, making it electrically conductive, can be fabricated into electrodes that destroy organic contaminants in water through an electrochemical process. Pharmaceutical compounds, pesticide residues, and industrial chemicals that pass through conventional water treatment systems intact are broken down at boron-doped diamond electrode surfaces with high efficiency. The technology exists. It has been demonstrated. Small-scale installations are already operational in Europe. The limitation, again, is the cost of the diamond substrate. At abundance, diamond electrode water purification would not be a specialized technology deployed only in wealthy municipalities. It would be standard infrastructure. All of this, the thermal conductivity, the hardness, the chemical inertness, the electrical properties when doped flows from one source, the tetrahedral lattice, 4 bonds, each one a strong covalent bond, no free electrons to carry electricity in pure form, but those same bonding electrons transfer vibrational energy, which is what heat is, at the atomic level, with extraordinary efficiency, because the lattice is so stiff and the bonds so short. The structure is so rigid that impurities can barely penetrate it. The atom-to-atom geometry is so perfect that sound waves, heat waves, and light all interact with it in ways that produce properties found nowhere else in the natural world. Everything extraordinary about a diamond traces back to one carbon atom, bonded to 4 neighbors, replicated with perfect regularity across a structure that can be as small as a grain of dust or as large as a fist. And here is the thing about that structure, that the jewelry industry never had much reason to advertise. It forms whenever the right conditions exist. Carbon plus sufficient pressure, plus sufficient temperature, held for long enough. Earth produces those conditions in a few specific places for geological reasons that are not particularly under human control. But the universe, as we are about to discover, produces those conditions in places that make Earth's diamond-forming regions look like a candle flame next to a nuclear reactor. The scarcity that built the diamond trade, the marketing that kept it alive, the cultural mythology that turned carbon into commitment, none of it is wrong. Exactly. It is just a story built in one place by people who had no idea what was happening 4.4 billion kilometers away. And now we do. So, let us go there. Because the next time you hear the words diamond rain, the correct response is not wonder that such a thing might exist. The correct response is wonder that we did not look more carefully at our own solar system sooner. The planets have been doing this for billions of years. They have not been waiting for our permission. Neptune is blue, not the pale, washed-out blue of Earth's oceans from above, but a vivid, saturated, almost electric blue, a color so deep and uniform that photographs of the planet look more like computer renderings than actual images. The color comes from methane in the upper atmosphere, which absorbs red wavelengths of sunlight and reflects blue ones back into space. Neptune is 8 times Earth's mass. Its diameter is nearly 4 times Earth's. It orbits the Sun at an average distance of approximately 4.4 billion kilometers. And because of that distance, sunlight arriving at Neptune is approximately 900 times dimmer than sunlight arriving at Earth. It is cold at the top. Temperatures in the upper atmosphere hover around -210 degrees Celsius. From those conditions alone, you might picture a quiet, frozen world, drifting in the dark at the edge of the solar system, not doing very much. That picture is wrong in almost every meaningful way. To understand what Neptune is actually doing, you have to stop thinking about the surface. You can see the visible cloud tops, the atmospheric bands, the storms, and think about what lies beneath. Neptune is classified as an ice giant, and that term is misleading in exactly the way that the most consequential scientific labels always are. It does not mean Neptune is covered in ice. It does not even mean the interior of Neptune is cold. What it means is that Neptune's bulk composition, beneath its outer hydrogen and helium atmosphere, is dominated by compounds that scientists call ices in their chemical sense, not their physical state. Water, ammonia, and methane are ices in this classification, regardless of whether they are actually frozen. Under the conditions inside Neptune, they are not frozen at all. They are compressed into states of matter that have no familiar analog on Earth's surface. Think of Neptune's interior as a series of layers, each one more extreme than the last as you descend. The outermost layer is the gaseous atmosphere you can photograph, hydrogen, helium, and that methane that gives Neptune its color. Below that is a transition region where pressure increases rapidly and gases become denser, hotter, and more fluid. Below that is what scientists call the mantle, a thick, deep layer of compressed water, ammonia, and methane in states that are simultaneously dense enough to be considered fluid and hot enough to be considered plasmas, neither solid nor liquid nor gas in any conventional sense. This mantle makes up the bulk of Neptune's mass. It extends for thousands of kilometers, and within it, under pressures that dwarf anything achievable by human technology and temperatures that would vaporize any metal we know, something is happening to the methane. Methane is a simple molecule. One carbon atom bonded to 4 hydrogen atoms, arranged in the same tetrahedral geometry that we already know is carbon's preferred structure, CH4. It is common, it is stable under ordinary conditions, and it is one of the most abundant carbon-bearing molecules in the outer solar system. But methane is only stable under ordinary conditions. When you compress methane to pressures of millions of atmospheres and heat it to temperatures of thousands of degrees Kelvin, the bonds that hold the hydrogen atoms to the carbon atom can no longer resist the mechanical and thermal forces acting on them. They break. The molecule dissociates. The hydrogen, being lighter and more mobile, migrates away through the surrounding fluid. The carbon atom, now liberated from its hydrogen partners, is surrounded by immense pressure and extreme heat, and it is looking for a new configuration. Under those conditions, carbon's most stable configuration is diamond. The same tetrahedral structure we discussed in part 1, the same 4-bond geometry, the same tight covalent lattice, but now forming not in a geological pocket 140 miles below Earth's surface, but throughout a layer of planetary interior, thousands of kilometers thick. The carbon crystallizes. Diamond nuclei form. They grow, and then, because diamond, even under these extreme conditions, is denser than the surrounding fluid, they begin to sink. Gravity pulls them downward through the interior, deeper and deeper into the planet, a slow and silent precipitation of carbon crystals that, in the context of human language and human experience, we can only call rain. This is not a metaphor. This is not a poetic interpretation of data. This is the mechanism that multiple independent lines of scientific evidence, theoretical models, computational simulations, and most critically, direct laboratory experiments support as the most plausible explanation for what is happening inside Neptune and Uranus right now. Let us be precise about the laboratory evidence, because precision is what separates scientific understanding from storytelling, and what makes this story worth telling. The key breakthrough in understanding diamond rain came from a series of experiments using high-powered lasers and diamond anvil cells. Ironic? Yes, that the instrument used to study diamond formation applies diamond itself to generate pressure. In these experiments, researchers took materials similar in composition to Neptune's and Uranus's mantles and subjected them to the kinds of pressure and temperature conditions that models predict exist deep inside those planets. The results were not ambiguous. Carbon compounds broke down and reformed as diamond. The diamond formation process could be observed directly in the laboratory in real time. But then came the 2024 experiment, and it changed the picture in a significant and specific way. In January of 2024, a team of researchers led by Mungo Frost at the SLAC National Accelerator Laboratory, working at the European X-ray Free Electron Laser Facility in Schönefeld, Germany, the most powerful X-ray laser facility on Earth, published results in the journal Nature Astronomy that refined our understanding of when and where this diamond formation begins. The team used a plastic film made of polystyrene, a hydrocarbon compound, meaning it contains carbon and hydrogen, just as methane does, just as Neptune's mantle does, and compressed it using intense shock waves driven by that X-ray laser. The compression achieved pressures and temperatures representative of conditions inside Neptune and Uranus at specific depth ranges. And they used X-ray diffraction in real time to watch what happened to the carbon atoms inside that compressed polystyrene film at the exact moment of compression. What they saw was nano-diamonds forming, not after waiting, not as a theoretical prediction. Right there, in the experimental chamber, carbon crystallizing into diamond structure under the imposed conditions, observable in real time through the X-ray diffraction pattern. This is experimental confirmation of a level that carries substantial scientific weight. It is not a simulation. It is not a model. It is carbon under planetary interior conditions, doing what the models predict it does, forming diamonds demonstrated directly in the laboratory. The critical new finding was this: the diamond formation began at lower pressures and lower temperatures than previous experiments had indicated. Earlier work suggested that diamond precipitation inside Neptune and Uranus required the most extreme conditions found deep within those planets. The 2024 XFEL results showed that the process begins at conditions corresponding to shallower depths than previously assumed. This means that the zone inside Neptune and Uranus, where diamond rain is actively forming, may be larger and extend closer to the outer layers of the planet than the previous models predicted. More of the planet's interior may be participating in this process. The diamond rain may be more extensive than the scientific community had estimated even a few years before these results were published. It is important to be clear about what the 2024 results do and do not establish. They confirm that diamond formation from hydrocarbon compounds occurs under the pressure and temperature conditions found inside Neptune and Uranus. They confirm that this formation begins at shallower depths than previously thought. What they do not directly confirm is the full picture of what happens to those diamonds afterward, whether they genuinely sink through the interior as a sustained rain, how large the diamonds grow, how fast they fall, or how the process unfolds over geological time. Those aspects of the story remain in the domain of strong scientific interpretation supported by models, not directly observed phenomena. The distinction matters. The science is strong. It is not yet complete. Now, to understand why diamonds sink, rather than staying suspended or dissolving back into the surrounding fluid, you need to understand something about density. Diamond, even at the pressures present inside Neptune, is denser than the fluid medium surrounding it. Just as a rock sinks through water not because it is pushed down, but simply because it is denser than the fluid it displaces, diamond crystals forming in Neptune's interior mantle sink downward through the surrounding compressed fluid. Gravity does the rest. This is not a dramatic event. It is not a catastrophic collapse. It is a slow, sustained sinking, a geological process operating over timescales that dwarf any human reference. Individual diamonds forming deep inside Neptune and sinking toward the planet's core are not racing through the interior. They are descending in the way that sediment descends through deep water, measured, relentless, and continuous over billions of years. As those diamonds sink, they pass through a layer that makes the story considerably more interesting than mere precipitation. Below the zone where diamonds form, models of Neptune and Uranus predict the existence of a layer of what scientists call superionic water. Superionic water is one of the stranger states of matter that extreme pressure and temperature can produce. In ordinary liquid water, both the oxygen and hydrogen atoms move freely, which is why water flows. In ordinary ice, both oxygen and hydrogen atoms are locked in place in a crystalline lattice, which is why ice is solid. In superionic water, the oxygen atoms lock into a crystalline lattice the way they do in ice, but the hydrogen ions, which are just bare protons once they lose their electrons, flow freely through the oxygen lattice the way ions flow through liquid water. The result is a material that is simultaneously crystalline and conducting a solid that carries electrical current as efficiently as a liquid electrolyte. It behaves like neither solid nor liquid, but like something that has no exact parallel in everyday experience. This layer of superionic water, predicted by models to exist at specific depth ranges inside Neptune and Uranus, is conducting. It carries electrical current. And when the sinking diamond crystals pass through this layer on their way deeper into the planetary interior, they disturb it. They drag against it. They create currents in the conductive fluid, the way a moving object creates currents in any fluid it passes through. Currents in a conducting fluid, in the presence of a rotating planetary body, generate magnetic fields. This is the same principle behind Earth's magnetic field, which arises from convective currents in the liquid iron nickel outer core. It is called dynamo action, and it is the fundamental mechanism by which most planets generate their magnetic fields. The currents do not have to be dramatic. They do not have to be fast. They just have to exist in a conducting medium, in a rotating body, for a sufficiently long time, and the currents stirred by sinking diamonds through a superionic water layer make to the leading scientific interpretation, clearly labeled as such, may be contributing to the generation of the magnetic fields of Neptune and Uranus. This brings us to one of the most genuinely puzzling facts in planetary science, and one that the diamond rain hypothesis may actually help explain. The magnetic fields of Neptune and Uranus are not like Earth's. Earth's magnetic field is roughly dipolar. It has a north magnetic pole and a south magnetic pole, tilted about 11 degrees from Earth's rotation axis, and it is broadly symmetric. The field is generated deep in the core, and extends outward in a pattern that, while complex in detail, is broadly predictable and well understood. Neptune's magnetic field is none of those things. It is tilted approximately 47 degrees from Neptune's rotation axis. It is dramatically offset from the center of the planet. The magnetic center of Neptune is displaced by more than half the planet's radius from its geometric center. The field is asymmetric and irregular in ways that no simple dipolar model can capture. Uranus is similarly bizarre. Its magnetic field is tilted approximately 60 degrees from its rotation axis, and it too is offset from the planetary center by a substantial fraction of the planet's radius. Both magnetic fields seem to be generated not at the deep core, as Earth's is, but somewhere within the planet's interior mantle, somewhere in the zone where superior ionic water layers exist. The diamond rain hypothesis offers a physically plausible mechanism for why these fields look the way they do. If the dynamo generating the magnetic field is not concentrated at a single deep core, but is instead distributed through a thick shell of superionic water being stirred by falling diamonds across a wide range of depths, the resulting magnetic field would be expected to be more complex, more asymmetric, and more offset from the planetary center than a simple core dynamo would produce. The irregularity of Neptune and Uranus's magnetic fields is not a problem to be explained away. It may be a fingerprint of a process, and the process may be the rain of precious stones through their interiors. This remains a candidate scientific explanation, not a confirmed one. Planetary science does not yet have the instruments to directly observe Neptune's interior or measure what is happening in its mantle in real time. The Voyager 2 spacecraft, which flew past Uranus in 1986 and Neptune in 1989, gave us the magnetic field measurements that revealed the strangeness of those fields. But Voyager 2 was not designed to probe planetary interiors. No mission since has visited either planet up close. The connection between diamond rain and magnetic field generation is a leading hypothesis, supported by the consistency between the diamond rain models and the known magnetic field geometries. It is taken seriously by planetary scientists. It is not yet proven. What is proven, or rather, what is experimentally confirmed to the extent that laboratory science can confirm anything about a planet it cannot directly sample, is that carbon compounds form diamonds under the pressure and temperature conditions found inside Neptune and Uranus. The 2024 XFEL experiment provided that confirmation with a degree of directness and precision that earlier experiments had not achieved. And the theoretical framework connecting diamond formation to magnetic field generation through the superionic water dynamo mechanism is coherent and physically well motivated, even if it awaits direct observational confirmation. Now step back for a moment from the details of the mechanism and sit with the magnitude of what is being described. Neptune has existed for approximately 4.5 billion years. The process of methane dissociation and diamond formation inside its mantle is not something that started last Tuesday. It has been operating continuously for essentially the entire history of the solar system. For 4.5 billion years, diamonds have been forming inside Neptune and sinking through its interior. Not in tiny quantities. Neptune's mantle contains enormous amounts of carbon in the form of methane and other hydrocarbon compounds. The mass of material participating in this process is, by any measure accessible to human intuition, incomprehensible. Scientific estimates of how much diamond precipitation might occur inside Neptune and Uranus vary depending on the specific model and the assumptions about the composition and structure of the mantle layers. But the orders of magnitude involved are not trivial. These are not tiny quantities of nanodiamonds forming in laboratory experiments. These are sustained geological processes operating inside planets that dwarf Earth in mass and interior volume, producing diamond crystals that, if the theoretical models are correct, grow as they fall, accreting additional carbon as they descend. In the same way that raindrops on Earth grow by collecting water vapor, as they fall and sinking over geological timescales toward whatever waits at the base of the diamond-forming zone. What waits at the base on Neptune and Uranus is not a surface in any familiar sense. There is no ground to hit. The diamonds sink until they reach a layer where pressure and temperature conditions no longer favor solid diamond, where other phases of carbon become more stable, or where the composition of the surrounding fluid changes enough that the diamonds stop growing and begin to dissolve or transform. The details of this terminus are still being worked out by planetary scientists. But the general picture is clear. Diamonds form, fall, and eventually incorporate into the deeper interior of the planet in ways that change the planet's composition, its density profile, its thermal evolution, and its magnetic field over billions of years. There is one more aspect of the 2024 results worth dwelling on, because it expands the implications of diamond rain beyond Neptune and Uranus. Specifically, the Frost team's findings showed that diamond formation from hydrocarbon compounds begins at lower pressures than previously thought. That has an immediate consequence for the classification of which planets might experience this process. Neptune and Uranus are not the only planets in the universe with masses and compositions in the relevant range. So-called mini-Neptunes, planets with masses between roughly 1 and 4 times Earth's mass, with compositions similar to Neptune and Uranus, are among the most common types of planet discovered orbiting other stars. The lower pressure threshold for diamond formation means that smaller versions of Neptune with lower interior pressures might also generate diamond rain. This is a genuine extension of the science, and Frost and colleagues noted it in their paper. This episode is focused on our own solar system, but the principle is worth naming. Diamond rain may be far more common across the universe than our solar system alone would suggest. Within our solar system, Neptune and Uranus are the primary sites of this process. The planets with the right composition, the right interior structure, and the right pressure and temperature profiles to sustain methane dissociation and diamond precipitation across a substantial portion of their interiors. They are not exotic curiosities. They are the third and fourth largest planets in the solar system by mass, 2 of the 8 planets that orbit the same star we orbit. They have been there since the solar system formed. The process we are describing has been happening continuously for the entire time Earth has existed. And while this has been going on, while Neptune has been raining diamonds through a mantle of compressed fluid, while the sinking crystals have been stirring the superionic water layer, while the resulting currents have been generating the bizarre, asymmetric magnetic field that Voyager 2 detected in 1989, human beings have been on Earth 4.4 billion kilometers away, constructing an entire cultural mythology around the occasional diamond that manages to form in Earth's comparatively mild geological conditions and survive the eruption that carries it to the surface. The De Beers cartel, the engagement ring campaign, a diamond is forever. The blood diamond trade that claimed lives across Sierra Leone, Angola, and the Democratic Republic of Congo as armed factions fought to control the mining of stones. All of it built on the geology of a single, ordinary planet that produces diamonds in quantities that, from Neptune's perspective, would barely register. But the strangeness does not stop with the precipitation itself. It extends into the specific physical conditions that shape this rain in ways that have no analog on Earth. On Earth, rain forms in clouds when water vapor condenses around tiny particles of dust or salt. A raindrop begins as a microscopic water cluster, grows as it collects vapor, and falls through the atmosphere until it hits a surface. The total journey from cloud base to ground is, in most weather events, a matter of a few kilometers, taking at most a few minutes. A raindrop is a temporary structure. It forms, falls, hits, and rejoins the water cycle. Diamond rain on Neptune operates on entirely different scales in every dimension that matters. A diamond nucleus forming in Neptune's mantle at a depth corresponding to significant pressure models suggests the diamond-forming zone may begin at depths of approximately 7,000 to 10,000 kilometers below the visible cloud tops, which is to say, depths that represent a substantial fraction of Neptune's total radius of about 24,600 kilometers is not a temporary structure. Diamond is not going to dissolve or evaporate on its way down. Once formed, under these conditions, it is stable. It falls not through a few kilometers of open air, but through thousands of kilometers of compressed fluid, over timescales that may be millions of years per individual crystal. Each crystal is not a raindrop. Each crystal is a geological event of its own, slow and inexorable, shaped by the physics of an environment that makes Earth's most extreme geological conditions look placid. The size of the diamonds forming inside Neptune is a subject of active scientific interest and some uncertainty. The laboratory nanodiamonds produced in the XFEL experiment were, as the name implies, nanoscale billions of times smaller than any gemstone, but those were formed in a laboratory experiment lasting nanoseconds, designed to demonstrate that the formation process occurs, not to replicate the full geological timescale over which crystals grow inside a planet. Inside Neptune, diamonds forming over millions of years and falling through thousands of kilometers of interior would have vastly more time to grow. Kevin Baines and Mona Delitsky, in their 2013 work on gas giant diamond formation, estimated that diamond hailstones forming in the interiors of Jupiter and Saturn might grow to what they called diamond bergs chunks, potentially centimeters across, that could be held in a human hand. For Neptune and Uranus, the models suggest that diamonds forming at depth and falling through the mantle could grow to sizes well beyond the nanoscale, though exactly how large remains an open question in the planetary science literature. The constraints on growth depend on the density of carbon in the surrounding fluid, the temperature gradient the diamond falls through, and whether the conditions remain favorable for crystal growth throughout the descent. These are active research questions, not settled facts. What is clear, and confirmed by the experimental evidence, is that the process is real, that it occurs in the pressure and temperature regime found inside these planets, and that it has been occurring for billions of years. The exact sizes, exact quantities, and exact fate of the resulting crystals at depth remain areas where models provide guidance, but direct observation is not yet possible. There is also the question of what, specifically, lies at the bottom of Neptune's diamond-forming zone below the region where diamonds remain stable and continue to grow. This is where the story touches the deepest and most speculative layer of the planetary interior. At sufficient depth, pressure and temperature may exceed the melting point of diamond, even under extreme compression. Diamond has a high melting point under ordinary conditions, but under the pressures of a planetary interior, the melting point can shift. If diamond melts at sufficient depth inside Neptune or Uranus, it would transition from a solid precipitate to a liquid carbon component of the deep interior fluid. The diamonds would not accumulate on a core surface in the way one might imagine. They would melt, incorporate, and become part of the planet's deep interior composition. This is consistent with the general picture of how icy planet interiors work. Rather than a clean, distinct separation between layers, there is a gradual transition in which materials become more and more compressed and more integrated into the surrounding planetary mass as depth increases. This picture diamond crystals forming in the upper mantle, growing as they fall, stirring the superionic water layer, and eventually melting into the deep interior, is the most complete account that current science, combining laboratory experiment and theoretical modeling, can offer for what Neptune and Uranus are doing right now. It is not a story built from imagination. Every component of it is connected to something measurable: the chemistry of methane dissociation under pressure, the crystal structure of diamond, the density of diamond relative to surrounding fluids, the electrical conductivity of superionic water, the measured magnetic field geometry of both planets. The hypothesis holds together because the physics holds together. The certainty with which individual components can be stated varies, but the overall picture is the most scientifically motivated account currently available. And sitting behind all of it, constant and undeniable, is the scale. Neptune alone has a mass approximately 17 times Earth's mass. Its interior occupies a volume that would contain more than 50 Earths stacked inside it. The mantle layer in which diamond formation is occurring is not a thin shell. It is a thick, continuous region thousands of kilometers deep, representing a large fraction of the planet's total volume. The amount of carbon available in that mantle, in the form of methane and other hydrocarbons, is staggering by any comparison to Earth's diamond-producing regions. This is not a boutique process. This is a planetary-scale chemical transformation operating continuously over geological time. If you tried to count the diamonds being produced inside Neptune over the course of a single Earth year, not cumulative since formation, just 1 year, the number would be meaningless in any unit that human experience provides a reference for. Diamonds per second would not help. Tons per year would not help. The physics of planetary interiors does not scale to the vocabulary of mining and carats. What we can say is that the process is happening, that it has been happening for as long as Earth has existed, and that the material it is producing is precisely the same tetrahedral carbon lattice that human beings have spent millennia treating as the rarest and most precious substance a person can acquire. That discrepancy between cosmic abundance and earthly scarcity, between Neptune's geological indifference and humanity's cultural obsession, is not a coincidence worth chuckling at. It is the lens through which the rest of this episode has to be understood. The next planet in our story does something even more extreme. Jupiter and Saturn take the diamonds that Neptune and Uranus produce in solid form and, in their own interiors, melt them. The gas giants are not simply raining diamonds. They may be sitting on top of oceans of them. Jupiter is not a planet in the way that Earth is a planet. That sentence requires unpacking, because the word planet implies a kind of solidity, a kind of comprehensible scale, a kind of geological architecture that Jupiter simply does not possess. Earth has a crust you can stand on. It has a mantle of rock that flows on geological timescales. It has an iron core that spins and generates a magnetic field. The boundaries between these layers are real, physical transitions from one kind of material to another. Jupiter has none of that. Jupiter is, from its outermost cloud tops inward, an almost unbroken gradient of gas becoming denser, hotter, and more compressed until, at depths where the pressure reaches somewhere between 1 and 2 million times Earth's atmospheric pressure, hydrogen, ordinary hydrogen, the simplest element in the universe, the element that makes up most of the sun, stops behaving like a gas and starts behaving like a metal. It conducts electricity. It flows. It becomes something that has no name in ordinary experience, and in that metallic hydrogen ocean, Jupiter generates the most powerful magnetic field of any planet in the solar system. Jupiter is not a rock with an atmosphere. Jupiter is, from top to bottom, atmosphere, in the sense that there is no surface, no boundary where gas stops and solid begins in any clean or definitive way. It is a world of continuous compression, continuous transition, continuous transformation of matter under forces that Earth's geology has never produced and never will. This matters enormously for understanding why diamond formation on Jupiter and Saturn works by an entirely different mechanism than diamond formation on Neptune and Uranus, and why the outcome of that mechanism, taken to its extreme conclusion by the conditions in those gas giant interiors, produces something that belongs in a different category of astonishment altogether. On Neptune and Uranus, the primary carbon source is methane locked into the mantle as a component of the compressed ice layer. The methane is there from the beginning, incorporated into the planet when it formed from the same cloud of gas and dust that built the entire solar system. The mechanism that liberates carbon from methane inside Neptune requires the extreme pressures and temperatures of the deep mantle conditions that are, in a meaningful sense, geologically deep and geologically quiet. The methane dissociates not because something dramatic is happening at that moment, but because the pressure and temperature of the mantle interior are simply high enough, continuously and permanently, to break the molecular bonds. Jupiter and Saturn start their diamond story at the surface. Or rather, they start it in the atmosphere, which on a gas giant is the only place they have. Both Jupiter and Saturn host atmospheric phenomena that make every weather system in Earth's history look modest by comparison. The storms on these planets are not meteorological events in any scale that Earth's history has produced. Jupiter's Great Red Spot is a storm system that has been continuously active for at least 350 years, possibly longer, and it is wide enough that 2 Earths could fit inside it side by side. Saturn's polar hexagon, a geometric storm system at Saturn's north pole with sides, each approximately 13,800 kilometers long, has been observed continuously since the Voyager missions in the pre-1980s and appears to be a stable, enduring atmospheric feature rather than a transient event. These planets have weather that lasts centuries. They have storm systems the size of continents, and within those storm systems, they have lightning. The lightning on Jupiter and Saturn is not comparable to the lightning on Earth in the way that saying they also have storms might imply. Earth lightning is produced by charge separation in water ice clouds, typically in systems where strong updrafts loft water droplets and ice crystals to high altitudes where they collide, separate charge, and eventually discharge in the familiar bolt of atmospheric electricity. The bolts on Earth carry energies of roughly 1 to 5 gigajoules, enormous by human engineering standards, capable of vaporizing trees and igniting buildings, but modest on a planetary scale. The lightning detected on Jupiter by the Galileo spacecraft and confirmed by subsequent observations from the Juno mission carries estimated energies approximately 1,000 times greater than typical Earth lightning. Saturn's lightning, detected by the Cassini spacecraft as radio emissions called Saturn electrostatic discharges, is similarly powerful, with some discharge events releasing energies in the range of billions of joules per pulse. These are not bolts of lightning in the way you picture lightning. These are atmospheric explosions of electrical energy happening continuously across the cloud layers of planets 10 times Earth's diameter. When a bolt of lightning with that energy density rips through an atmosphere that contains methane and other hydrocarbon compounds, and both Jupiter and Saturn have detectable methane in their upper atmospheres, it does not simply ionize the air around it and recombine. It tears apart the hydrocarbon molecules. The carbon atoms are liberated from their hydrogen partners by the sheer violence of the electrical discharge. But, unlike the situation inside Neptune's mantle, where the liberated carbon is immediately surrounded by millions of atmospheres of pressure, the carbon liberated by atmospheric lightning on Jupiter and Saturn finds itself initially in a low-pressure environment, the upper atmosphere, where pressures are comparable to or even lower than Earth's surface pressure. At low pressure and high temperature, liberated carbon atoms tend to form graphite rather than diamond. Graphite is the other major crystalline form of carbon, the material in pencil leads, the material used in nuclear reactors as a neutron moderator, the material that forms the basis of graphene. Where diamond arranges its carbon atoms in three-dimensional tetrahedral bonds in all directions, graphite arranges them in flat hexagonal sheets that are bonded weakly to each other and strongly within each sheet. Graphite is stable at low pressure. Diamond is stable at high pressure. The carbon liberated by lightning in Jupiter and Saturn's upper atmospheres initially forms graphite specifically. It forms tiny particles of graphite soot, the same sooty carbon that collects in the exhaust pipe of a poorly tuned engine, that blackens the inside of a chimney, that forms on the wick of a candle flame. This was the key insight developed by the planetary scientists Kevin Baines of the University of Wisconsin-Madison and Mona Delitsky of California Specialty Engineering, whose work was presented to the Division for Planetary Sciences of the American Astronomical Society in 2013. The process they outlined begins with those graphite soot particles forming in the upper atmosphere from lightning-processed hydrocarbons. The soot particles are tiny, beginning, in Baines and Delitsky's estimates, at approximately 1 micrometer in diameter. They are also denser than the surrounding atmospheric gas. So they fall, not fast, not dramatically, but steadily, drawn downward by gravity into the deeper layers of the atmosphere. As the soot particles fall, two things change simultaneously. Pressure increases and temperature increases. Both Jupiter and Saturn have substantial atmospheric pressure gradients. The deeper you go, the higher the pressure climbs, rapidly and continuously. At depths where pressure reaches tens of thousands of atmospheres, far shallower than the conditions inside Neptune's mantle, but still extreme by any Earth standard, the graphite soot undergoes what material scientists call Neptune's phase transition. The hexagonal sheet structure of graphite, stable at low pressure, becomes less stable relative to the three-dimensional tetrahedral lattice of diamond. The carbon atoms rearrange. The soot, falling through increasing pressure, transforms into diamond. The diamonds then continue to fall, growing as they go. Baines and Delitsky estimated that the diamonds growing as they fall through Jupiter and Saturn's atmospheres might reach sizes of approximately a centimeter or more. By the time they reach deeper layers, chunks large enough to hold, large enough to feel the weight of, large enough that the word diamond in the sense of a gemstone rather than a powder becomes applicable. They coined the term diamondbergs for the largest of these falling crystals, extending the weather metaphor diamond hailstones, diamond rain, diamondbergs falling through the interior of a gas giant. The terminology has a playful quality, but the underlying physics is serious and grounded in the thermodynamics of carbon phase transitions. It must be stated clearly. The Baines-Delitsky scenario is a hypothesis presented at a scientific conference, supported by physical reasoning and atmospheric modeling, but it has not undergone the same kind of direct experimental confirmation that the Frost team's 2024 XFEL results provided for diamond formation inside Neptune and Uranus. The mechanism is physically plausible and consistent with what is known about carbon phase transitions and the interior conditions of Jupiter and Saturn. It has been widely cited and discussed in the planetary science community, but it does not carry the same experimental weight as a directly observed laboratory result. On Saturn specifically, Baines estimated that the process might produce on the order of 1,000 tons of diamond per year, a figure that rests on assumptions about lightning frequency, hydrocarbon abundance, and conversion efficiency that cannot currently be verified by direct observation. Treat this as a leading scientific hypothesis, motivated by solid physical reasoning, not as a confirmed measurement. What is confirmed, and has been confirmed for decades, is the interior structure of Jupiter and Saturn at a level sufficient to reason about what would happen to a falling diamond. And this is where the story of gas giant diamonds diverges sharply from the story of ice giant diamonds, and where it arrives at its most spectacular and its most speculative conclusion. Diamond has a melting point. Under ordinary conditions at Earth's surface pressure, diamond does not actually melt, it converts directly to graphite vapor before reaching a liquid state, sublimating rather than melting. But under sufficiently high pressure, diamond's melting point becomes real and measurable, and it rises with increasing pressure up to a point. Experimental measurements using shock, compression, and static high-pressure diamond anvil cells have established that at pressures above approximately 10 million atmospheres, diamond melts into liquid carbon. The liquid carbon that results is a metallic fluid, electrically conducting, dense, and unlike any liquid found under ordinary conditions. The question then is whether the pressures inside Jupiter and Saturn reach the threshold where falling diamonds would melt. And the answer, based on models of those planets' interior structures, is yes, at depths corresponding to the lower atmospheric layers and the transition region between the outer gas envelope and the deeper metallic hydrogen interior. Pressures likely exceed the values at which carbon's diamond phase becomes unstable in favor of liquid carbon. The diamonds falling through Jupiter and Saturn's interiors would, according to this picture, eventually reach a depth where the pressure and temperature conditions cause them to melt. And if they melt, they do not simply dissolve into the surrounding hydrogen. Liquid carbon, liquid diamond, to use the more evocative term, is denser than the metallic hydrogen environment it would be melting into. It would not mix homogeneously, it would pool. It would collect at the pressure and temperature conditions found at specific depths inside Jupiter and Saturn. The models suggest that liquid carbon could form a stable, stratified layer, an ocean of liquid diamond, resting beneath the falling diamond precipitation above it, held in place by its own density and the pressure equilibrium of the surrounding planet. This is the picture that captures the imagination most forcefully, and it deserves the label it carries: speculative interpretation grounded in physical reasoning. The thermodynamics are consistent. The density arguments are coherent. The interior pressure and temperature profiles of Jupiter and Saturn, derived from spacecraft observations and gravitational field measurements, are real and reasonably well constrained. Whether liquid diamond actually pools into a stable ocean at specific depth intervals inside these planets is a theoretical prediction, not a confirmed observation. No instrument has ever been inside Jupiter deep enough to observe this layer directly. No measurement from orbit has yet been able to probe the interior at the depth resolution needed to confirm the presence of a liquid carbon layer. The Juno spacecraft, which has been orbiting Jupiter since 2016 and has provided extraordinary new data about Jupiter's gravity field, atmospheric dynamics, and magnetic field structure, cannot currently resolve the chemical composition of the deep interior at the layer where diamond melting would be expected to occur. What Juno has done is dramatically improve our understanding of Jupiter's interior structure in ways that are relevant to this story. Juno's gravity measurements have revealed that Jupiter's interior is not divided into clean, distinct layers in the way that older simplified models assumed. The transition from the outer molecular hydrogen envelope to the deeper metallic hydrogen region is gradual rather than abrupt. The core, if Jupiter can be said to have a core in any conventional sense, appears to be a diluted, diffuse region where heavy elements are mixed into the hydrogen rather than concentrated in a distinct solid ball. This complexity is important because it means that the conditions under which liquid carbon would form and potentially pool are themselves distributed across a range of depths rather than occurring at a sharp boundary. The diamond rain story inside Jupiter is not a story of a tidy layer where diamonds melt and collect. It is a story of a complex interior where carbon is undergoing continuous transformation across a gradient of conditions. Saturn's interior is, in some ways, better constrained and, in some ways, more uncertain. Saturn is less massive than Jupiter, approximately 95 times Earth's mass compared to Jupiter's 318 times Earth's mass, and its interior pressure profile is correspondingly lower. The threshold at which carbon's diamond phase might melt into liquid is reached at greater depth inside Saturn than inside Jupiter, and the temperature gradient in Saturn's interior places the melting zone in a region of the planet that is harder to probe remotely. Saturn's ring system, as spectacular as it is for what it tells us about the outer planet, does not help us peer inside the planet's deep interior. The Cassini spacecraft's grand finale maneuvers in 2017, in which it made a series of close passes between Saturn and its rings before its deliberate atmospheric entry, provided new data on Saturn's gravity field and magnetic field that continue to be analyzed. Some of that analysis has refined models of Saturn's interior structure, but the question of liquid carbon layers remains in the domain of theoretical prediction rather than observational confirmation. Nevertheless, the interior conditions of both Jupiter and Saturn, as best as current science can characterize them, are consistent with the physical processes described by the Baines-Delitzky hypothesis. Carbon enters the atmosphere from hydrocarbon compounds and lightning processing. It falls as graphite soot. It converts to diamond at intermediate depths under increasing pressure. It continues to fall, growing as it descends. At sufficient depth, pressure and temperature exceed the diamond melting point, and it transitions to liquid carbon. Whether that liquid carbon pools into a stable ocean at a specific depth, flows slowly through the metallic hydrogen medium, or is gradually absorbed into the broader interior chemistry, depends on details of the planetary interior that are not yet fully resolved. The estimates of diamond production on Saturn that Baines and Delitzky offered, approximately 1,000 tons per year, are illuminating, not because they are precise, but because they put the process in a context that makes its implications clear. Saturn has existed for approximately 4.5 billion years. Even if the rate of diamond production has varied over that time as the planet's atmospheric chemistry evolved, the cumulative amount of carbon that may have passed through the diamond phase inside Saturn over its history is extraordinary. Whether that carbon now resides as diamond at intermediate depths, as liquid carbon at deeper depths, or as carbon dissolved into the metallic hydrogen interior depends on the details of the interior thermodynamics. But the carbon is in there. It has been cycling through extreme conditions for billions of years. The diamond story inside Jupiter and Saturn is not a story about a rare event. It is a story about a continuous, planetary scale chemical process that has been operating since these planets formed. There is one additional dimension to the gas giant diamond story that receives less attention than the rain itself, but that connects directly to the broader theme of what these planets are telling us about carbon's behavior under extreme conditions. Both Jupiter and Saturn radiate more energy into space than they receive from the Sunday. This is known and has been measured. Jupiter emits approximately 1.7 times as much energy as it receives. Saturn emits approximately 1.8 times as much. The standard explanation for this excess energy is the Kelvin-Helmholtz mechanism, a slow gravitational contraction of the planet's interior that converts gravitational potential energy into heat. As the planet contracts, and gas giant contraction is extremely slow by human standards. Measured in millimeters per year, the material falling inward converts potential energy to thermal energy, which eventually radiates outward as the excess heat we observe. For Jupiter, the Kelvin-Helmholtz mechanism explains the observed heat excess reasonably well. For Saturn, it does not. Saturn emits more excess heat than the Kelvin-Helmholtz mechanism alone can account for, given Saturn's age and mass. Something inside Saturn is generating additional heat. One proposed explanation, not the only one, but a physically interesting one, involves the differentiation of helium from hydrogen inside Saturn's deep interior. Helium, being denser than the metallic hydrogen surrounding it, may be raining out of the hydrogen-helium mixture in the deep interior, sinking toward the center and releasing gravitational energy as heat. This helium rain hypothesis is supported by the observation that Saturn's atmosphere appears to be depleted in helium relative to what the solar nebula, the cloud of gas from which the solar system formed, would have provided. The helium in this picture has sunk out of the upper atmosphere and into the deep interior. The relevance to diamonds is conceptual rather than mechanistic. Both processes, helium rain and diamond rain, represent examples of planetary interiors undergoing compositional differentiation over geological time, with denser components sinking and releasing energy As they do so, Saturn may be, in a very real sense, a planet that is raining multiple substances simultaneously: helium from the metallic hydrogen layer, diamonds from the atmospheric carbon, and perhaps other components of its interior chemistry, cycling through the extreme conditions of its interior in ways we have not yet fully characterized. The interior of Saturn is not a static structure. It is a dynamic system, slowly sorting itself by density over billions of years, and the diamond precipitation is one component of that sorting process. Jupiter, by contrast, appears to be less dramatically. Losing helium, its heat balance is better explained by contraction alone, but the scale of Jupiter's interior makes the diamond story there arguably even more staggering in its implication. Jupiter's interior pressure at the center is estimated at approximately 40 million to 60 million atmospheres. At those pressures, essentially all the carbon that reaches the deep interior is going to behave in ways that have no analog in Earth's geological experience. Whether it melts, solidifies, or transforms into exotic high-pressure phases of carbon that laboratory experiments have only begun to characterize, is an active area of research in high-pressure physics. Every year, new experiments using progressively more powerful laser compression facilities push the boundaries of what is known about carbon's behavior under extreme pressure. The 2024 XFEL experiment was one step in that ongoing program. More steps will follow. What is already known from the combination of atmospheric observations, spacecraft gravity measurements, high-pressure laboratory experiments, and theoretical modeling paints a picture that is coherent, physically grounded, and genuinely extraordinary. Jupiter and Saturn are not simply large planets with atmospheres. They are chemical engines processing carbon continuously, driven by the energy of lightning, fed by the rich hydrocarbon chemistry of their atmospheres, and operating across interior pressures that compress that carbon through phase transitions of a kind that Earth's geological processes have never achieved. Diamond is one of the products. The interior conditions that destroy diamond, melting it, transforming it, are just as real as the conditions that create it. And somewhere in the interior of Jupiter and Saturn, possibly right now, liquid carbon may be pooling in layers thousands of kilometers wide, sitting in a pressure equilibrium beneath the falling diamond hail above and the metallic hydrogen ocean below, forming the largest diamond ocean that physics allows, one that no human instrument has ever reached, one that no mission currently planned will ever directly sample, one that exists purely by inference from physics and chemistry applied to planetary structures, understood through measurements made from orbit. The contrast with Neptune and Uranus could not be sharper. Inside the ice giants, diamond forms in a mantle of compressed hydrocarbons and sinks as solid crystals through a layer of superionic water, stirring currents that may generate those planets' bizarre magnetic fields. Inside the gas giants, diamond forms from atmospheric soot, grows as it falls through increasing pressure, and at sufficient depth melts into a liquid that may constitute the strangest and most massive body of liquid in the solar system. Two different planets, two different mechanisms, two different outcomes, the same element, the same tetrahedral arrangement of atoms at every point where diamond exists, before the conditions destroy it. Carbon, doing what carbon does under pressure, in four different worlds, in four different ways, none of which require any of the cultural apparatus that human beings have constructed around the rare and beautiful stones that occasionally reach Earth's surface. Neptune's diamonds never see the light. Jupiter's diamonds melt before they can accumulate. Saturn's atmospheric diamonds convert from soot so slowly and fall so far before melting that the journey is a geological epic compressed into something the size of a hailstone. And Uranus, tilted on its side, its magnetic field more dramatically offset and tilted than any other planets. Its interior, the least well characterized of the four, sits quietly in the outer solar system, doing its own version of this process, generating its own version of this rain, holding its secrets behind a surface that no spacecraft has visited since Voyager 2 flew past in 1986. We have sent probes to Mars. We have landed on the Moon 12 times. We have dropped a probe into Jupiter's upper atmosphere, where it survived for approximately 58 minutes before being destroyed by pressure and heat. We have not returned to Uranus. We have not returned to Neptune. The last close look we took at either of them was with a spacecraft launched in 1977, and that spacecraft passed by in the 1980s and moved on. There are proposals, serious, scientifically motivated proposals for dedicated ice giant missions that would orbit Uranus or Neptune for years and characterize their interiors, magnetic fields, and atmospheric chemistry with modern instruments vastly more capable than anything Voyager carried. Those missions have not yet been approved and funded. The planets that may hold the most extraordinary precipitation process in the solar system remain, in 2025, largely unexplored. That absence of data is not a reason to dismiss the hypothesis. It is a reason to build the missions. But it is also a reminder of how much of the most important science in the solar system is still waiting for the first close look. The four planets that rain diamonds are, in the most direct sense, our neighbors. They formed from the same cloud of gas and dust that formed Earth. They orbit the same star. They have been there, doing what they do, for longer than complex life has existed on Earth. And we have looked at them closely, in the sense of sending a spacecraft within range of their magnetospheres, exactly twice each, once for Jupiter and Saturn with Voyager, and again for Jupiter with Galileo and Juno, once for Uranus and Neptune with Voyager, and never again. The diamond rain falling inside them has been doing so, silently and continuously, through all of human history and all of human prehistory and all of the billions of years before any human stood upright on a savanna and looked up at a night sky full of unfamiliar stars. That continuity, 4.5 billion years of planetary process, operating regardless of whether anyone was watching, regardless of whether anyone had the mathematics to describe it, regardless of whether the carbon crystallizing in Neptune's mantle had ever been named or noticed, will carry us into the final movement of this story. Because the diamond rain is not just a fact about distant planets, it is a mirror. And what it reflects, when you hold it up to Earth, changes how you see everything that happens here. The thought experiment has been waiting since part 1. Now it is time to follow it to its conclusion. Start with a single kilogram of rough diamond. Not cut, not polished, not graded for color and clarity, not placed in a velvet case under museum lighting. Just rough carbon crystals, the way they come out of the ground in the Juaning mine in Botswana or the Udakni pipe in Russia, lumpy, unpolished, not particularly beautiful to look at, carrying the same physical properties that make gemstones extraordinary, regardless of how they appear before cutting. 1 kilogram of rough diamond, wholesale, trades on the international diamond market at prices that vary by quality, but that for gem-grade stones run into the hundreds of thousands of dollars. For industrial-grade rough stones, substantially less, but still measured in hundreds to thousands of dollars per carat, and 1 kilogram is 5,000 carats. the cheapest industrial diamond powder, the most processed and least pure form of diamond material available in commercial quantities, costs roughly a few $100s per kilogram. A kilogram of granite gravel used as construction aggregate costs approximately 2 to 4 cents. Now, imagine that the geological accident that makes diamonds rare on Earth, the specific combination of depth, temperature, pressure, ancient volcanic eruption, and survival through the journey from mantle to surface had never happened. Or rather, imagine that it happened so frequently, so continuously, and at such enormous scale that diamonds were simply a component of the mineral landscape, not a curiosity, not a treasure, a material, something you would find in a riverbed alongside quartz and feldspar, something you would haul away in dump trucks and sort by size, something that cost per kilogram approximately what granite costs per kilogram, 2 cents a kilogram. That is the thought experiment. The physics does not change. The tetrahedral lattice does not change. The Mohs 10 rating does not change. The thermal conductivity does not change. The chemical inertness does not change. Every property that makes diamond extraordinary as a material persists, regardless of what it costs. The only thing that changes when diamonds become common is the decision about when and where to use them. Right now, the decision is made by price, and the answer is almost always only in the most specialized applications where nothing else will do. When diamond costs 2 cents a kilogram, the decision is made purely by whether diamond's properties serve the application better than any alternative. And in that case, the answer changes for an enormous range of applications simultaneously. Let us follow that change through, in order of increasing consequence. The most immediate and most physical change is in construction. Concrete is the most widely used construction material in the world by volume. Approximately 4.4 billion tons of concrete are produced globally every year. The basic formula has not changed substantially since the Romans used a form of it to build the Pantheon. Aggregates gravel, sand, crushed stone bound together by a cementitious matrix. The aggregate makes up approximately 60 to 75% of concrete's total volume. Its properties directly affect the concrete's compressive strength, its resistance to cracking, its ability to withstand vibration and impact. Harder aggregate, with better bonding to the cement matrix, produces stronger concrete. Right now, the hardest aggregate used in conventional construction is crushed granite, which sits at approximately 6 to 7 on the Mohs scale. Diamond sits at 10, 3 full-scale increments above granite, representing an exponentially greater resistance to deformation and abrasion. Diamond aggregate mixed into concrete would not simply make the concrete slightly stronger. It would create a category change in what reinforced concrete structures can resist. Compression tests of materials show that the strength of the aggregate limits the ultimate strength of the concrete matrix. You cannot make the matrix stronger than the aggregate that constrains it. With diamond aggregate, the limiting factor shifts entirely to the cement binder and the reinforcing steel, both of which can be independently optimized. Structures built with diamond aggregate would resist seismic loading in ways that conventional concrete structures cannot. The frictional interface between diamond particles and the cement matrix diamond's hardness means the particles resist being dislodged under stress, creates a bonding geometry superior to any conventional aggregate. For earthquake-prone regions, for high-rise structures in seismic zones, for bridges and dams and tunnels and foundations where failure is measured in lives lost, The material improvement is not incremental. It is fundamental. Diamond powder, mixed into road surfaces, changes the friction characteristics of pavement in ways that are immediately relevant to safety. The stopping distance of a vehicle on wet pavement is dominated by the friction coefficient between the tire and the road surface. Road surfaces become slippery when the aggregate particles in the asphalt wear down and expose the smoother binder below. Diamond particles embedded in road aggregate would not wear down under traffic. They would maintain their geometry and their surface texture essentially indefinitely. Roads surfaced with diamond aggregate would maintain consistent, high friction coefficients across their entire service life, rather than degrading as the surface wears. Wet weather braking distances would shrink. Ice on a diamond aggregate road surface would have a harder time bonding because the surface texture would remain sharp rather than polishing smooth. Runways, where landing aircraft generate some of the highest friction demands of any surface application, would benefit directly and dramatically. These are not exotic applications. These are applications that road engineers and materials scientists already understand and would implement immediately if cost were not the barrier. The barrier is entirely cost. At 2 cents per kilogram for diamond aggregate, every kilometer of new highway would use diamond-reinforced asphalt as a matter of standard specification. Within a generation of cheap diamonds, the character of infrastructure globally, its durability, its safety performance, its maintenance interval, would shift substantially and permanently upward. Now, move to the application with the most consequence for how people live their daily lives. Electronics. The thermal conductivity story was established in Part 1, but its implications for computing deserve deeper treatment because the engineering constraint it addresses is not abstract. Modern computing architectures are in a period sometimes called the dark silicon era, a reference to the fact that chip designers can now etch more transistors onto a given area of silicon than they can power simultaneously without exceeding safe thermal limits. The transistors are there. The switching speed is theoretically available, but running all of them at full speed simultaneously would generate enough heat to destroy the chip within milliseconds. So chip designers leave portions of the chip powered down at any given moment, dark silicon cycling through different sections to manage the thermal load. This is not a software problem. It is not a design problem in the conventional sense. It is a materials problem. The thermal conductivity of the chip substrate and the heat sink are not sufficient to remove heat as fast as full chip operation would generate it. Diamond's thermal conductivity, approximately 2,200 watts per meter per Kelvin for natural diamond, rising to approximately 3,320 watts per meter per Kelvin for isotopically pure carbon-12 diamond, is not just better than copper's 400 watts per meter per Kelvin. It is categorically different in its implications for thermal management. A chip substrate made of diamond or a chip bonded to a diamond heat spreader of sufficient quality would conduct heat away from transistors fast enough that the dark silicon constraint would shrink substantially. More of the chip's transistors could operate simultaneously because more of the heat they generate could be carried away in real time. Computing performance, not theoretical transistor count, but actual delivered performance, would improve in ways that no other materials substitution could achieve. This is not speculation about a distant future. It is an extrapolation of a technology that already works in the laboratory and in specialized commercial applications. Diamond heat spreaders are currently used in high-power semiconductor lasers, in certain military and aerospace electronics, in radio frequency power amplifiers for telecommunications infrastructure. They are used where the thermal problem is severe enough and the application valuable enough that the extraordinary cost of diamond can be justified. The transition to cheap diamond does not require inventing a new technology. It requires making an existing, confirmed, working technology available at the scale and cost that allows it to be used universally, rather than only where failure is catastrophic enough to justify any expenditure. At 2 cents per kilogram for diamond, the economics of chip design change completely. Diamond substrates for processors would not be a premium option for defense applications. They would be the standard substrate for all high-performance computing. Data centers, which currently consume approximately 1 to 2% of global electricity, a substantial fraction of which goes not to computation but to cooling, would redesign their thermal management architecture around diamond heat spreaders that are smaller, lighter, and far more effective than copper heat pipes and aluminum heat sinks. The energy saved in cooling alone, applied across global data center infrastructure, would represent a meaningful reduction in electricity consumption at planetary scale. Smartphones and laptops would shrink, or their batteries would last longer, depending on which design priority manufacturers chose. Both outcomes follow from the same physical improvement: less energy wasted as heat, more energy available for computation, or stored in a battery that does not need to spend itself running cooling systems. The diamond thermal conductivity improvement to computing is not a marginal gain. It is the resolution of a fundamental physical constraint that is currently limiting the progress of one of the most consequential technologies in human civilization. Medical applications deserve their own accounting, because the consequences there are measured not in efficiency gains, but in outcomes for human bodies. Diamond scalpels, blades in which a diamond edge provides the cutting surface rather than steel, are not new. They have been used in specialized ophthalmological surgery, particularly in procedures requiring incisions of extraordinary precision in delicate tissues. A diamond blade can be sharpened to an edge approaching single-atom sharpness, a physical geometry that steel simply cannot achieve because steel's crystalline structure has a grain size that sets a lower limit on how sharp the edge can be made. A diamond edge, being a single crystal with perfectly ordered atomic geometry, can be honed to a level of sharpness that no metal can match. This matters in surgery not just for precision but for tissue response. Sharper cuts produce smaller inflammatory responses, heal more cleanly, and leave less scar tissue than the micro tears produced by edges that are blunt at the atomic scale. Currently, the use of diamond surgical tools is confined by cost to the few procedures where the precision benefit is significant enough and the volume of procedures low enough that diamond instruments can be shared, resharpened, and amortized across many uses. Cataract surgery, certain corneal procedures, some neurosurgical applications. If diamond costs 2 cents per kilogram, every hospital in the world uses diamond instruments as standard equipment, not as a luxury, not as a capability reserved for the best-funded medical centers. As a baseline expectation, the way that the sterilized steel scalpel is a baseline expectation today. Surgical outcomes measured in healing speed, infection rate, scar formation, and postoperative complication rates would improve globally and immediately for any procedure where incision quality matters, which is to say, essentially all surgery. Diamond electrodes for water purification sit at a different point in the technology adoption curve. one where the engineering is even more mature, but the scale of global benefit is potentially even larger. Boron-doped diamond electrodes produce hydroxyl radicals among the most chemically reactive species known at their surface when an electrical current passes through them. These hydroxyl radicals destroy organic molecules in the water flowing past the electrode, pharmaceutical compounds, pesticide residues, industrial dyes, endocrine-disrupting chemicals, and antibiotic-resistant organic compounds that pass through conventional biological water treatment without being broken down. The boron-doped diamond electrode does not discriminate. It attacks essentially all organic pollutants with equal chemical aggression, breaking their molecular bonds and converting them to carbon dioxide and water. Pharmaceutical contamination of drinking water sources is an emerging global problem with no widely deployed solution. Antibiotics, synthetic hormones, antidepressants, and chemotherapy drugs pass through human bodies and through municipal wastewater treatment, largely intact, enter rivers and groundwater, and accumulate in drinking water supplies. Conventional water treatment is designed around biological processes that take time and rely on microbial communities that cannot destroy many of these synthetic compounds. Diamond electrode electrochemical treatment is fast, does not require biological communities, does not produce toxic byproducts, and handles essentially the full spectrum of organic contaminants. It already works. Small installations already operate. The constraint, again, is the cost of producing boron-doped diamond electrodes in the quantities needed for municipal water treatment at any meaningful scale. At diamond's commodity price, under our thought experiment, every municipal water treatment facility adds diamond electrode electrochemical treatment as a final polishing step. Global pharmaceutical contamination of drinking water, a problem currently affecting hundreds of millions of people with essentially no deployed solution, becomes tractable. Drilling is perhaps the most economically straightforward application, but it is worth pausing on because the scale of its consequence is easy to underestimate. Diamond-tipped drill bits are already used in mining, in oil and gas extraction, in geothermal well drilling, and in construction. They are used because diamond cuts through rock faster, more cleanly, and with less wear than any alternative. A drill bit that would wear out in hours using tungsten carbide inserts will last days or weeks with diamond-tipped geometry. The cost of diamond tips is the reason that diamond-equipped drilling is reserved for applications where the drilling rate and tool longevity justify the material cost. At 2 cents per kilogram for diamond, every drill bit used in every hard rock mining operation, every oil well, every geothermal installation, every tunnel boring machine, every construction core drill uses diamond as the cutting element as a matter of basic economics. The productivity improvement in extractive industries and tunneling would be substantial, not marginal. The kind of deep geothermal energy access that currently requires drilling through formations so hard that drill bit replacement dominates project costs becomes dramatically more economically competitive. This is where the thought experiment connects to something that the Diamond Rain story makes visceral rather than theoretical: the relationship between material scarcity and human capability. Every limitation described above, the imperfect surgery, the computing chip that cannot use all its transistors simultaneously, the water that carries pharmaceutical contaminants, the construction aggregate that cracks under seismic loading, is a real problem with a known solution that is currently unavailable at scale because of a material price. Diamond is the solution, or part of the solution. In each case, the material exists, the technology works. The barrier is cost, and cost is a function of scarcity, and scarcity is a function of the specific geological accident of how carbon behaves inside Earth. Contrast that with Neptune, where the scarcity does not exist. There is no geological lottery inside Neptune. There is no kimberlite pipe erupting at exactly the right speed to carry crystals to the surface before they graphitize. There is no De Beers cartel deciding how many carats reach the market this quarter. There is no cultural narrative about forever and commitment and the worthiness of a partner measured in faceted carbon. There is just methane under pressure, doing what methane does, breaking apart, liberating carbon, which then does what carbon does under pressure, arranging itself into a tetrahedral lattice and falling. Neptune has no opinion about what that material is worth. It has been generating it continuously for 4.5 billion years. And here is the thing about that juxtaposition that demands to be sat with rather than passed through quickly. The diamond is not different inside Neptune. The carbon is the same. The bonds are the same. The geometry is the same. The thermal conductivity of a diamond crystal forming inside Neptune's mantle is the same 2,200 watts per meter per Kelvin that makes diamond the best thermal conductor of any solid at room temperature here. The Mohs hardness is 10 there, as it is here. The chemical inertness that makes diamond electrode water purification possible is a property of the tetrahedral lattice structure, regardless of which planet produced the lattice. The physical object is identical in every scientifically meaningful way. What is different is everything that surrounds the object: the rarity, the mythology, the cartel, the advertising campaign, the cultural weight of a four-word slogan that convinced most of the Western world that the appropriate expression of romantic commitment is a gemstone controlled by a monopoly. Adam Smith wrote about this in 1776 in The Wealth of Nations, in a passage that has been called the diamond water paradox. He observed that water essential to life, required by every living thing, without which civilization is impossible, is nearly free, while diamonds with scarce any value in practical use command extraordinary prices. The paradox seems to violate some intuitive principle that useful things should be more valuable than useless things. Smith used it to illustrate the distinction between use value and exchange value. The price a thing commands in the market is not determined by how useful it is, but by how scarce it is relative to demand. Water was nearly free in 18th century England because it was abundant. Diamond was expensive because it was rare. The utility of the object and the price of the object were almost independent. What Smith could not have known, because the industrial applications of diamond had barely been imagined in 1776, is that his example had a hidden dimension. Diamond is not, in fact, without practical value. It has extraordinary practical value. It has the highest hardness of any natural material. It has the best thermal conductivity of any solid at room temperature. It is chemically inert in environments that destroy metals and corrode ceramics. It can be made into a surgical edge sharper than any steel. It can be made into an electrode that destroys organic contaminants in water. It can be embedded in road surfaces to maintain friction for the lifetime of the road. It can be used as a heat spreader that allows processes to run faster than any copper-based thermal management system permits. The paradox Smith identified was not simply that an impractical luxury was priced above a practical necessity. The paradox was deeper than he knew. The impractical luxury was also, simultaneously, the most practically useful solid material that chemistry allows. It just could not be used practically because it was too rare. The price, enforced by the scarcity, enforced by the geology, prevented the utility from being accessed. Smith was right about the mechanism, and unknowingly wrong about the material's actual utility. Now, the thought experiment reveals its full shape. If Neptune's abundance were somehow transplanted to Earth, if carbon crystallized into diamonds the way it does inside that distant blue planet, and those diamonds were as common as the gravel you can pick up from any riverbed, Adam Smith's paradox would not simply be resolved, it would be inverted. Diamond would not become worthless. It would become one of the most valuable construction and technology materials in human civilization, deployed at scale, embedded in every structure and every device that benefits from its properties. It would be worth not the astronomical prices of a gemstone market built on artificial scarcity, but the substantial and real value of a material that makes buildings earthquake-resistant, that lets chips run faster, that makes surgery cleaner, that makes clean water accessible, that makes drilling faster. It would be worth what it is actually capable of, which turns out to be rather a lot, just not in the currency of engagement rings. There is a quality to this realization that is difficult to name precisely, but that is worth trying to articulate, because it is the emotional destination that the entire episode has been building toward. It is not simply irony, though there is irony in abundance. It is not simply wonder, though wonder is present. It is something closer to a correction of perspective, a reorientation of how to look at the relationship between human valuation systems and physical reality. The universe does not consult our price tags before doing chemistry. Carbon inside Neptune is not aware that humans have decided that carbon arranged in a tetrahedral lattice is worth more per gram than almost any other substance on Earth. The planetary interiors do not adjust their output based on the De Beers cartel's quarterly production targets. The 4 planets in our solar system that are producing diamonds through 2 entirely different mechanisms, at scales that dwarf any geological process Earth has ever hosted, have been doing this continuously and indifferently for 4.5 billion years, and they will continue to do it for billions of years more, regardless of what any human civilization does or decides or values or destroys. This is not a council of insignificance. It is not an argument that human value systems are simply wrong and should be abandoned in favor of some purer, more cosmic perspective. Human beings value things for reasons rooted in their experience, their history, their emotional lives, and the social structures they build and inhabit. The fact that diamonds have been rare on Earth is a genuine fact about Earth's geology, and the cultural significance that accrued to that rarity is not manufactured from nothing. It is built on a real physical condition, even if the market was then deliberately manipulated to maintain and exploit that condition. The mythology around diamonds is not simply a lie. It is a human response to scarcity, amplified by an industry that understood how to make that response serve its commercial interests. But the solar system does not care about any of that. And knowing that the solar system does not care, knowing that Neptune has been raining diamonds through its interior since before complex life existed on Earth, knowing that Saturn may be producing 1,000 tons of diamonds per year through atmospheric lightning and carbon phase transitions, knowing that Jupiter may contain a liquid diamond ocean deeper than any drilling technology will ever reach, does something to the mythology. It does not destroy it, exactly, but it changes its context. It places the mythology inside a larger frame, and in that larger frame, the mythology becomes smaller. Not worthless, but smaller. More precisely, what it actually is: a human story built in a human context about a human experience of scarcity, not a cosmic truth about the value of a material, not an objective verdict from the universe on what carbon is worth when it bonds to four neighbors. Just a story, shaped by geology and history and marketing, that we told each other for a few thousand years on a small planet, while four other planets in the same solar system went on doing what carbon does, quietly and at scale, with no audience and no opinion. The people who have most honestly understood this, historically, are not the geologists or the chemists or the planetary scientists. They are the industrial engineers, the people who work not with the mythology of diamonds, but with the actual properties. The people who specify diamond-tipped drill bits and measure their performance in meters per hour of rock penetrated. The people who design diamond heat spreaders and measure their performance in watts per meter per Kelvin of heat removed. The people who operate boron-doped diamond electrode water treatment systems and measure their performance in the concentration of pharmaceutical contaminants destroyed per kilowatt hour of electricity consumed. These people do not talk about forever. They do not talk about carats. They talk about hardness, thermal conductivity, chemical inertness, crystallographic purity, and cost per unit area of electrode surface. They use the same material that fills jewelry boxes and museum displays, and they use it as what it actually is: a tool. The best tool in certain applications. The one that no other material can substitute for. The one that costs too much to use everywhere it would be useful. Neptune does not find this ironic. Neptune does not find anything. That is rather the point. The planetary interior that may be producing more diamond in a single year than Earth has produced in its entire geological history has no experience of diamonds as precious, no experience of diamonds as romantic, no experience of diamonds as anything at all. It simply has methane under pressure, and methane under pressure becomes carbon, and carbon under those conditions becomes diamond, and diamond is denser than the surrounding fluid, and denser things sink. That is the complete story from Neptune's perspective. 4 sentences. 4 billion years. What takes 4 sentences from Neptune's perspective has taken civilizations millennia to understand, and cost real suffering in the process. The blood diamond trade diamonds mined in conflict zones and sold to finance armed factions, responsible for funding wars in Sierra Leone, Angola, Liberia, and the Democratic Republic of Congo, costing hundreds of thousands of lives, exists because diamonds are valuable enough to be worth fighting over. The value comes from the scarcity. The scarcity comes from the geology and the cartel. The cartel was constructed because a small number of people understood, before most people did, that the mythology of diamonds could be leveraged into enormous wealth if the supply of diamonds could be controlled. All of that, all of the history, all of the suffering, all of the corporate strategy and cultural engineering traces back, ultimately, to the fact that Earth's interior does not produce diamonds the way Neptune's does. Earth is stingy with carbon. Neptune is not. This is the fact that the thought experiment illuminates most sharply, not the happy version, the version where diamonds are cheap and buildings are stronger and chips run faster and water is cleaner. That version is true and worth dwelling on, and we have. But the sobering version underneath it is equally true. Every real-world harm that the diamond trade has produced across human history is traceable, in its deepest structure, to a planetary lottery. Earth happened to form in a way that produces diamonds rarely enough for them to be genuinely scarce. Had Earth formed more like Neptune, had its mantle contained more methane, had its interior pressures been distributed differently, had the geological processes that transport diamonds to the surface been more frequent, the entire apparatus of scarcity, mythology, and exploitation that surrounds diamonds would have had no foundation on which to build. There would have been no Kimberley mines to monopolize. There would have been no cartel to construct. There would have been no cultural engineering required, because the engineering would have been pointless. You cannot build a mythology of rarity around a material that everyone can pick up from a riverbed. We did not get Neptune's geology. We got Earth's, and on Earth, the lottery produced scarcity, and scarcity produced value, and value produced everything that followed, the beauty and the brutality of it, the romance and the violence, the museum displays and the conflicts. Carbon, arranged in a tetrahedral lattice, did not choose any of that. The universe did not arrange it. It was simply what happened on this particular planet, in this particular inner solar system, with this particular mixture of geological processes operating over this particular span of time. Neptune has been raining diamonds for 4.5 billion years. Earth has been raining the mythology of diamonds for approximately 5,000 years, which is, from Neptune's perspective, so brief as to be immeasurable. 5,000 years of human diamond culture is to 4.5 billion years of Neptunian diamond precipitation what a single heartbeat is to a human lifetime. And even that comparison is too generous to the human timeline by several orders of magnitude. The disproportion is not just large, it is of a kind that challenges the categories through which we normally compare things. And yet, from inside human experience, from inside the timeline where the 5,000 years of diamond mythology is all there is, the myths feel ancient and fundamental and real. They feel like they touch something true about love and permanence and beauty. They feel, in the moment of looking at a cut gemstone in a ray of light, justified, the flash of color from a well-cut facet, the way white light separates into its component spectrum as it bends through the material's high refractive index, is genuinely beautiful. The stone is genuinely extraordinary. The material really is the hardest, most thermally conductive, most chemically inert solid that chemistry has produced through natural means. The ore that human beings have directed toward diamonds across all of history is not misplaced ore, it is just incompletely aimed. It stops at the surface of the stone at the sparkle, the rarity, the symbol, and does not follow the physics inward to where the real wonder lives, in the tetrahedral lattice that carbon builds when it has no choice but to be its most organized self, and in the fact that 4 planets in our own solar system are building that structure right now at scales that no human civilization and no human industry and no geological process on Earth has ever approached. That is the stone that built empires of scarcity. That is the stone falling through the interiors of Neptune, Uranus, Jupiter, and Saturn in 4 different ways, through 4 different mechanisms, toward 4 different fates. That is the stone that, if it were as common as sand, would remake human infrastructure, human medicine, human computing, and human access to clean water, not because we would have invented new science, but because we would finally be free to use the science we already have. The universe built the best solid thermal conductor ever measured. It built the hardest natural substance ever identified. It built a material so chemically stable that it barely reacts with anything, so crystallographically perfect that a human hair placed across a single crystal reflects clearly in the geometry of the facets, so optically magnificent that scattered light inside it separates into every color simultaneously. It built this material from the most common element in organic chemistry, using pressure as the only tool. It placed that process inside 4 planets that orbit our Sunday. It has been running that process continuously, without pause, for 4.5 billion years. And we found one of the rare instances where a piece of that process reached Earth's surface and survived, and we put it in a ring. The planets have no objection to that. They do not have objections. They have pressure and chemistry and time, and they have been making diamonds from all 3 quietly, continuously, on a scale we are only beginning to understand, since long before anyone on Earth knew there was anything to make.